So they want you to plot the displacement time graph for this particle P here as this wave pulse with this shape moves towards that particle P. Okay, so an easy way to look at this would be, let's just say, for example, you have a graph of displacement time, right? So you try to imagine what happens. This wave profile, the one that I've highlighted in pink here, will gradually move towards the right. So if, let's just say right now it looks like this, a short instant of time later, it will look like this. And then another short instant of time later, it will look like this. Okay, so you look at which part of this wave will reach point P first. Okay, so if I rub off everything now, which part of this wave pulse will actually reach point P first? You will see that it is actually this point that will reach point P first. This one could be it will be this part of the wave that reaches point P at t equals to 0. And then it will be this part that reaches point P at t equals to 1. This part reaches at t equals to 2. And then this part at t equals to 3, t equals to 4, and then t equals to 5. Okay, so from here you try to trace out the displacement or the graphs according to the time that you have. So at t equals to 0, this one, if I look at it from the equilibrium position, this one will be the displacement, so it will be over here. At t equals to 1, this is the displacement, so it will be over here. At t equals to 2, it's the same, it will be over that same displacement. And then at t equals to 3, it will be here. T equals to 4, it will be downwards like this. And then t equals to 5, you'll go back to the original shape. So if you trace out the shape, it actually looks like this. So the original shape should have been, which one is the shape? Yeah, it's supposed to be a bit a 0 here first, actually. Okay, the timing, maybe I got it wrong a little. I should have started from here, t equals to 0 actually. So this part will go here first. Right, let me just redraw that shape. Okay, like this. Okay, so maybe I don't do it like this. Maybe I change the timing. I try to mark out a few points at different timings. T equals to 0, t equals to 1, 2, 3, 4, 5, and 6. So I now try to trace out the displacement at that particular time. This part at t equals to 0 will reach here first, so it's here. This part will reach this point at t equals to 1. This part will reach this point at t equals to 2. This part will again reach this point at t equals to 3. And then this part will reach point P at t equals to 4. And then you repeat the same for the subsequent points. This is actually the shape that you will get. Okay. The answer is actually D, right? You have to kind of visualize what happens when this wave pulse goes towards the right. So you think of it this way, which part of this wave will hit particle P first? So when that part hits particle P first, particle P will displace according to that point. And so if you try to trace it out one by one, it should be answer D. Okay.
Okay, thank you.
All right. Okay. So just try to do it like that, and then you should be fine. right? So what I'll say here is there anything I can write here? Wait on, let me just write all of everything. Let me see whether I can write something here. It's the explanation. Plot displacement time graph for this particle. To do this question, what I will say is sorry. Let me just find out how to do this. I'll just say look at which part of the pulse reaches particle P first. Okay. Then plot the displacement from that. Okay. So basically what I just did was that you look at which part of the pulse reaches particle P first, then plot the displacement from that. All right. As the pulse travels through, plot the displacement from there as the pulse travels through P. Okay, which is basically what I did here. All right, so if this one is okay, then I will just resume with the next part of the lesson. All right. Okay. All right, so I'll clear off everything here. Okay, I'll just refer back to the notes. That one will be under page 5 of the notes. All right. So the thing that we haven't done was phase difference. Okay. Now phase difference, you will have two different kinds of phase difference. One is phase difference between two waves, and another is phase difference between two particles on the same wave. Okay, right. The start of the phase difference is actually on page 4, not page 5, sorry. Okay, now phase difference have two types: phase difference between two particles on the same wave, or phase difference between two waves. That is on the next page. Now let's just talk about what is phase difference in the first place. Phase difference between two particles on the same wave just refers to the fraction of a cycle by which one particle will lead or lag the other. The first thing that should come to mind when we mention to you about phase difference is that it always relates to how different in terms of a fraction of a cycle are 2 points. All right, that's in layman terms what it means. How different is two particles in terms of one cycle. All right, that's why we call it fraction of a cycle by which one particle leads or lags the other. Now, to determine phase difference, you can determine it from either a displacement time or a displacement distance graph. All right. So that time I mentioned to you, wave motion can be represented by two types of graph. Either it is displacement time or displacement distance graph. Regardless of which graph it is, you will be able to determine phase difference. So some of the steps that you will need to do when determining phase difference between two particles on the same wave will be following what I've just written here. What you just need to do is that you need to determine the difference between the 2 points on the wave. It could be in terms of distance, it could be in terms of time. It depends on what graph you were given. It will be in terms of distance if you're given a displacement distance graph. It will be in terms of time if you're given a displacement time graph. Okay, so once you determine the difference between those 2 points, what we'll need to do is to compare the difference with respect to the value of one complete cycle in order to see how much of a fraction of a cycle it is. And then from there, you express the fraction in terms of degrees or pi radians, because we know that one cycle is equal to 360 degrees or 2 pi radian. So let's see some examples here. If you look at the graph below here, there are two different graphs. One is a displacement time, one is a displacement distance graph. Okay, so say for example, I want to determine the phase difference between points A and B. Okay, so in terms of how different are those 2 points, I know that this is 1.25 seconds because you see, this one is one complete waveform. This one is already written here as 5 seconds. I know that this complete waveform can be divided into 4 equal portions. All right, so each one of these is actually going to be 1.25. This one, half of the complete waveform is 2.5. Another half of it will be 1.25. Okay, so therefore I know the difference between point A and point B will be 1.25 seconds. So for one complete cycle, I know it is worth 5 seconds. So what I want to do now is that I want to find this difference in terms of fraction of a cycle. So what I'll do is that I'll say it's 1.25 over 5. This one will give me the fraction of a cycle that it is in. So I want to convert it to a different unit. I know that one cycle is 360 degrees or 2 pi radian. So what I do is that I multiply that fraction that I have with 360 degrees, giving me 90 degrees. All right. So you can repeat the analysis for the subsequent points also. A with C. If you're talking about phase difference between A and C, the difference between those 2 points is 2.5 seconds. Compared with respect to one cycle is over 5. This is already the fraction of the cycle. So I want to convert it to degrees. I multiply with 360, I get 180. Okay, so you can do the same for A with D or A with E. You will still get the way to get the phase difference is still the same. All right, so this one is for displacement time. If you're talking about displacement distance, it's also the same method. All right, all you just need to do is to find the difference between 2 points compared with respect to one cycle. So say for example, right now I want to compare between A and C. The difference between these 2 points is 1 meter. Is half of 2 meter because you see this one is again one complete waveform here. So this one cycle is already written here as 2 meter. So if I divide this by half, I get 1 meter here. So I'm interested in the phase difference between points A and C. The difference is 1 meter. Compared with respect to one cycle, I get half a cycle. So I want to change it to degrees. Just multiply with 360, I get 180 degrees. All right. So again, you can do the same method for A with B, A with C, A with D, A with E. All right, you will still get the same answer. Now, in the event that you want to change it to units of pi radian, all you need to do is that you just need to multiply with 2 pi instead. Okay. So let's just say, for example, if I look back at the first example here, to find the phase difference between points A and B, I know it's a quarter of a cycle in terms of the phase difference, but I want to express it in terms of pi radian. So all you need to do is that you multiply with 2 pi, and then what you get is pi over 2 radians. Okay, so this is how you will convert it to pi radian. All right. Now, when you have particles or points that have phase difference of 0 or 360 degrees, we will normally call them as being in phase with each other. All right, so like in your case here, points A and E, for both of the graphs, they had a phase difference of 360 degrees. They're actually considered to be in phase with each other. Okay, and then when you talk about the phase difference between point B and D, which is this and this, we will normally say that the phase difference is 180 degrees or pi radian. Okay, out of phase here, a lot of time it normally means 180 degrees phase difference, because you see this one is B and then this one is D. If I just look at it as a whole, just looking at it like this is one cycle. This one is half a cycle. This one, just by looking at it without doing any calculation, I already know the phase difference is half a cycle, which when converted to degrees is going to be 180 degrees. Okay, so here we say point B and D are out of phase. The phase difference between point B and D is pi or 180 degrees. At these 2 points, when they're out of phase, both of the particles will actually start to move in the opposite direction. They have the same displacement, but they'll be moving in opposite direction. So if I try to draw the wave profile of short instance of time later, this particle will start to move down, this particle will start to move up. When they are out of phase, 180 degrees out of phase, they will be at the same displacement, but they will be moving in completely opposite directions. Okay, so that is one part here. Okay, what about if, yep, sorry.
So does that mean A and C are out of phase as well?
A and C, yes, they're also considered to be 180 degrees out of phase.
Okay. All right. Thank you.
Because you see, if I try to extend this line here, you see that A will go down, C will go up. They are again at the same displacement, but the way they'll move is completely opposite. All right. All right. Okay. So this one is okay. Then this is for phase difference between two particles. Now, usually when they ask you to find the phase difference between two particles, we will give you the particles to consider. We will tell you which particles to consider, which point to consider. All right. Now, then we move on to phase difference between two waves. All right. The previous one was you looking at one wave and comparing between 2 points. Now we have two waves. We compare the phase difference between two waves. Now, phase difference between two waves shares a similar meaning with phase difference between 2 points on a wave. We will say that phase difference between two waves is just a fraction of a cycle by which one wave leads or lags the other. It is still talking about how different the two waves are in terms of fraction of a cycle. So again, you can either determine them from a displacement time or displacement distance graph, but there is some slight difference here right now, and you want to find out the phase difference. What you will need to do when you're doing phase difference between two waves is that you will need to select points on each wave that are similar or in phase with each other. So when we say points that are similar, in phase with each other, it normally means something like this: crest and crest, or trough and trough, or equilibrium going downwards with equilibrium going downwards. So I'll show you what I mean by that later on. So the one thing that is different here compared to the previous one is that for phase difference between two waves, you normally need to select the points yourself. We won't tell you which point to select. You have to select the points yourself. So the key here is to select points that are similar or in phase to each other. Usually you will either select crest and crest, trough, or the equilibrium going downwards or equilibrium going upwards. All right. So after you've selected the points, the method is the same as the previous one. You will determine the difference between the two similar points, either in terms of distance or time, compare the difference with respect to the value of one complete cycle in order to determine how much of a fraction of a cycle it is, and then express the fraction in terms of degrees or pi radians, knowing that one cycle is 360 degrees and 2 pi radian. All right. So another thing here that you need to know is that the two waves that we give you may not have the same wave amplitude, but it won't affect the phase difference. It doesn't affect anything about the determination of phase difference. All right. Different wave amplitudes do not affect the phase difference. It doesn't affect the value of phase difference that you get. So if you look downwards, there are two diagrams here, a displacement time and a displacement distance graph for two different waves, waves A and waves B. All right. So notice that they don't have the same amplitude, but that one is not an issue because amplitudes being different does not affect phase difference. Okay, so right now you have the two different waves here. Right now, I want to determine the phase difference between these two waves. So you will first need to select 2 points that are similar to each other, all right, on the waves. So say, for example, if for wave X, which is the red wave, I select a crest, on the other wave, wave B, I must also select a crest, which is this point. So these are the two similar points. So I find the difference between these two similar points. I found out that it is 2.5 seconds. And then I want to relate it to the value of one complete cycle. If you look at the blue colored wave, this is already one complete cycle. So the 10 seconds is one cycle. All right. Okay. Should not have drawn the red colored line there, right? So this part here, I know is one full cycle, right? This 10 second here is one cycle. So the phase difference between the two waves now, if I pick the crest as my reference point, it will be 2.5 over 10. This one will give me the fraction of a cycle it is. It is 1/4 of a cycle. I change to degrees, multiply with 360, I get 90. All right. Now I could also pick different points on the wave, not necessarily the crest. I just need to make sure that the points are similar to each other. So maybe say I want to pick the trough position right now. If I wanted to pick the trough position, I could pick this point. Maybe I use a different shape. I could pick this position and also this position. I pick the trough position for wave B, the red colored wave, and then I pick the trough position for the blue colored wave also. This one are also the two similar points. So eventually, if I do some maths on this, I know that this one is also going to be 2.5 seconds. Compare this with respect to one cycle, I will also get a quarter cycle. Change to degrees, I will get 90 degrees. Okay. Right. So you can pick any points as long as the points are similar to each other. Crest and crest, trough or trough, it doesn't matter. Okay. Now, when it comes to finding phase difference between two waves, you may have two different values of phase difference. All right. Just now, if you refer back to what I did, the red colored wave, I picked the crest position. The blue colored wave, I also picked the crest position, right? All right. Now, this portion here represents one phase difference. There's also another phase difference, which is here. You see, if for the blue colored wave, I pick the crest position, the red colored wave, I also had to pick a crest position. It could have been this, or it could have been this. All right, this one here. Because you see the blue colored wave, I already picked the crest position. On the red colored wave, I must also pick a crest position. The first one that I picked was this. I could also pick this one as my reference point because they are still both similar or in phase with each other. So for these 2 points here, the phase difference will be 7.5 divided by 10, giving me 3/4 of a cycle. Again, change to degrees, multiply with 360, I get 270 degrees. All right. So bear in mind that phase difference can have two different values. All right. And then another thing that you will notice here is this. This one is a quarter of a cycle. This one is 3/4 of a cycle. If I add them up, it becomes one full cycle. And then this one is 90 degrees. This one is 270 degrees. If I add them up, it becomes 360 degrees. So you see, you can have two different phase difference, but once you add them up, it actually gives you back the whole full cycle. All right, so let's just say you are able to find the phase difference between two ways of a certain value. If you want to find the other corresponding value, all you just need to do is you just take one cycle minus the fraction, or 360 degree minus the fraction, or 2 pi radian minus the fraction itself. Okay, or 2 pi radian minus whatever you have in pi radian, sorry. Okay, so this is how you determine phase difference between two ways for displacement time graph. Now for displacement distance graph, it's still the same thing, okay? Just pick 2 points that are similar to each other, find out the difference between the 2 points, and then compare with respect to one full cycle, and you get the answer. All right, the method is the same, okay? Now, if you move on to page 6, all right, these are some examples here. Now, you have a wave here with all the points indicated. We want you to find out what are the phase differences between all those given points. Now, what is the phase difference between points O and A? Okay, now this one we didn't give you any values to work with, but from looking at the waveform itself, you should be able to see how much of a fraction of a cycle are those 2 points different by. All right, so you see this one is 1 cycle. I can clearly see that this one is 1 cycle. So this 1 cycle can be clearly divided into 4 equal parts. So if I'm talking about point A and B, this one I know is definitely a quarter of a cycle. So what's the phase difference between points A and B? I can say that the phase difference is a quarter of a cycle is a quarter of 360, giving me 90 degrees. So this one I know. Then which point is in phase with D? Okay. You need to find out a point which has a phase difference of 360 degrees with D. All right. Or zero phase difference with D. Okay, phase difference of 0 with D. But here, this one is more relevant to find a point where you have a phase difference of 360 degrees. Okay, phase difference of 360 degrees. Find a point that has a phase difference of 360 degrees with D. That one would be this one, isn't it? Okay, this one, phase difference of 360 degree or one complete cycle, if you would. All right, so this one, point O has a phase difference of 1 cycle with D, or 360 degrees, if you would. So this one, the phase point that is in phase with D is point O. Okay. If I give you another point F, this one also has a phase difference of 1 cycle. It could also be point F if you wanted to. All right. Basically, just see that it has a phase difference of 1 cycle. That one will be in phase already, because at those 2 points, both particles have the same displacement. They're also going in the same direction of motion. All right. It's different from the 180 degrees out of phase just now. The 180 degrees out of phase just now, I said the 2 particles are having the same displacement, but they're moving in completely opposite directions. But when you are talking about particles in phase, those 2 particles have the same displacement, but they're moving in exactly the same direction. All right, so that one, just bear that in mind. Okay, now what is the phase difference between points O and C? Okay, between points O and C, this one you can see is actually 1/4, 2 quarters, 3 quarters. So this one is having a phase difference of 3 quarters. So your phase difference is actually 3/4 of a cycle, giving you 3/4 times 360, 270 degrees. All right, so this one is okay. Now, moving on to the next point, which point has a phase difference of pi with A? Pi here would mean a 180-degree phase difference. Okay, if you add 2 pi, sorry, the color isn't that clear. If you have 2 pi radian, then it's 360. If you have pi radian, the phase difference must be 180 degrees. So if you're looking at a point that has a phase difference of pi with A, pi here having a phase difference of 180 degrees or half a cycle, you look at point A is this one here. Which point is half a cycle different than A? It will be this one. This one is half cycle, right? A quarter plus with a quarter gives me half cycle. So point C will be having a phase difference of pi with A. Okay. And then the last one would be, what is the phase difference between points B and D? B and D is this one and this one. So again, if you try to look at it carefully, they are actually 1/4, 2/4 here. This one is half cycle. So phase difference is actually half a cycle, giving me half of 360, giving me 180 degrees. Okay, so this is roughly how you can see phase difference. If they don't give you values to look at, unlike the previous examples, you can always just try and see from the waveform itself. Usually the waveform itself can be divided into 4 equal parts, like the ones that you see here. And then from there, you try to make the relation. All right, okay, so this part should be fine. Okay, then the next one I want to go through is question 2. All right, so I'll just clear the drawing here. Now, 2 light waves of the same frequency are represented by the diagram. What could be the phase difference between the 2 waves? All right, 2 light waves, same frequency represented by the diagram. What could be the phase difference between the 2 waves? The previous example was talking about phase difference between particles on the same wave. The current example here, number 2, is talking about phase difference between 2 waves. Okay, so this one, the first thing you would want to do is to pick 2 points that are similar to each other on each wave. So there's the blue colored wave and the red colored wave. Okay, so right now you want to pick a point that is similar to each other. So a good place to pick would be a crest. Okay, so let's just say I pick a crest on the red colored wave. Okay, this one I pick a crest on the red colored wave, which is this one. So the blue colored wave, I can also pick a crest. I must also pick a crest. Since the red colored wave, I've already picked a crest as my reference point. On the other wave, I must also pick a crest as my reference. So it could be this one or this one. Okay, so now my phase difference could be represented by these 2. Okay, this one is my phase difference. So now how would I find out what is the phase difference? Now you see this part here is 1 cycle. If you just look at the blue colored wave, this is actually 1 cycle corresponding to 360 degrees. All right, so this wave can be divided again into 4 equal parts. So now when you look at this point and this point, it's actually correct to say it's a quarter of a cycle, which in turn corresponds to 90 degrees. All right. Now, since I know the phase difference between these two already is 90 degrees, how will I find out the phase difference for this part? So remember I told you that the two values of phase difference would normally add up to give you back one complete cycle. It will give you back 360 just now. So if you already found out the phase difference for one point being 360 degrees, you want to find the phase difference for the other side, you just be, let me choose a suitable color. It'll just be 360 minus 90, giving you 270 degrees. Okay, so here your phase difference is either 90 degrees or 270 degrees. All right, so this part is for this. So this one, maybe I just write here. First phase difference. This one is for the first one. This one is for the second one. This is the second phase difference. Right? So there you have it. 90 or 270 degrees. Okay, so this part should be okay. Then after that, I move on to a bit more stuff before I start to do the past years for you. Okay, so this one is all right. And then I clear off whatever you have here. Okay, now, if you move on to the next page, page 7, wave speed V. Now, you know that waves move from one end to another end. So if they move, they must have a certain speed. All right. So from IGCSE, you have known that there's one equation that always relates wave speed. That one is actually V is equals to F lambda. And in your syllabus, you're required to know a little how they derive V equals to F lambda. Okay. So the derivation for V equals to F lambda is required in your syllabus. It's actually very simple. What you just need to remember is that for one complete oscillation, the distance traveled by a wavefront or a crest is equal to the wavelength, and the time taken is usually the period t. So if I use the equation speed equals to distance over time in symbol form, I will get v equals to lambda over t. Since distance traveled is equivalent to lambda and time is equivalent to the period, that's why I get this. All right. And then I also know that since f is equals to the reciprocal of t, I eventually get this. Because if I look at this one is v equals to, sorry, this one is also equivalent to 1 over t times lambda. So since f is equals to 1 over t, I will get back this. All right. Okay, then another thing here that I should mention here is that for any wave that travels in the same medium, if you have a wave that travels in the same medium, it will always have the same speed regardless of its frequency. Okay, so what I mean by that is that if let's say you have sound waves, okay, and it's traveling through air, for example, okay, it could have maybe say a frequency of 50 hertz for one particular sound wave. And then another sound wave could have a frequency of say 200 hertz. But because they're traveling inside the same medium, the speed is the same. Okay, both would have same speed. For any waves that is still traveling inside the same medium, they will always have the same speed regardless of the frequency. Frequency can change, but the speed itself will never change. All right. So here I actually give you a different example. EM radiation, all types of EM radiation will always have same speed regardless of the frequency in vacuum. Later on, you'll see that there are different types of EM radiation with different frequencies, different wavelengths, but they all always have the same speed because they're all still traveling inside the same medium. All right. So that one is okay. Okay, then the next one you may not have heard of before is intensity. Okay, intensity is, I think, new for your case. Intensity, I, is the energy per unit time per unit area, or rather is power per unit area. Intensity is a measure of the energy of the wave. If you want to think it another way, it's a measure of the energy of the wave. Okay, it is defined as energy per unit time per unit area. If you've gone through energy power chapter already, energy per unit time is actually power. So that's why we can also say is power per unit area, in other words. Okay, so the units of intensity is watt per meter square. It is actually derived from this definition, power per unit area. Power is unit of watt, area is unit of meter square. So power per unit area would have watt per meter square. So looking at how the intensity I is defined, equation Y looks like this. Energy per unit time per unit area, or power per unit area. Okay. Now, the most important thing that you will need to know from this is this relation. Okay. Intensity is proportional to amplitude square. All right. Such that later on you can do some calculations where you say I2 over I1 is equals to A2 square over A1 square. This is the most important thing you need to remember from here. All right. Okay, intensity could also be related to other parameters, but they are no longer in your syllabus. It will be given or mentioned to you in the question if you're required to use it. Okay. One thing we will tell you is that intensity tends to decrease with distance. What we mean by that is that if let's just say that this is your source of wave, you emit a wave, the wave travels a certain distance r. The thing here is that the further the distance, the weaker the wave, because more energy is lost. Okay, as your wave travels from say point A all the way to point B, you will lose energy along the way. So the further you travel, the weaker your wave. Okay, the weaker your wave will be. That's why here we tell you that there's a relation where intensity decreases with distance squared, which in turn will give you this relation. I2 to I1 is R1 squared to R2 squared. All right. The last relation is this: intensity is proportional to frequency squared. The higher the frequency of your wave, the more energy it carries. It's also having a squared term. So I is proportional to frequency squared, such that I2 to I1 is frequency 2 squared to frequency 1 squared. Okay, but this entire thing here, don't worry about it. You are not required to memorize this. If you need to use this, we will give it to you inside the question. The one that you really need to know is this one. Intensity is proportional to amplitude squared. Okay, so we've done quite a fair bit here. Let's just go through some questions. Let's have a look at, say, page 1. Okay. I think we can do this already. Right, just have a look at page 1. I'll go through some questions with you. All right. Okay, page 1, the first question. A sound wave moves with speed 320 meters per second through air. The variation with time of the displacement of an air particle due to the wave is shown. Which statement about the sound wave is correct? Right. This question actually has a bit to do with what you learned in the previous lesson. Now, which of this statement is the correct one? Let's try and see this one by one. This is a displacement time graph. So obviously I know that this is the period. The period is 4 milliseconds. So if I know the period is 4 milliseconds, I can find the frequency. frequency being the reciprocal of the period, 1 divided by 4 times 10 power minus 3. You're going to get 250 hertz. So if they tell you frequency of the wave is 500 hertz, this is obviously wrong. It should be 250 seconds. That's 250 hertz. Sorry. Okay. And then after that, if you look at the second answer choice, the graph shows that the sound is a transverse wave. Okay. So remember, one of the first thing I mentioned to you last week was that if you just look at the displacement time and the displacement distance graph, they won't tell you whether it's a transverse or longitudinal wave because they have exactly the same shape. So here, the graph shows that sound is a transverse wave. What you can say is that displacement time graph cannot be used to distinguish between transverse and longitudinal. Okay, this is fact number 1. Displacement time graph cannot be used to distinguish between transverse and longitudinal. And then there's also something wrong with this. This is a sound wave. Sound wave is known to be longitudinal. Okay, this one here, if they say the graph shows that the sound is a transverse wave, something is not making sense here. Sound is longitudinal wave. Longitudinal wave. Okay, so B in itself actually doesn't make sense whatsoever. You cannot use a graph to see whether it's transverse or longitudinal, and in the first place, sound wave is longitudinal. It is not transverse. So B is also out, is incorrect, A is out. Now, then after that, we tell you, let's look at part C. The intensity of the wave will be doubled if amplitude is increased to 0.4 millimeter. Okay, this is where what I just mentioned comes into play. Intensity and amplitude is related by this relation. Intensity is proportional to amplitude squared. All right. So you see, the amplitude is 0.4 millimeter. The amplitude is increased to 0.4 millimeter. The original amplitude is 0.2 millimeter. This tells you that the amplitude is doubled. Okay. Now, when it comes to looking at relations that look like this, there are actually 2 ways to go about it. All right. There's an easy way and there's a slightly more tedious way. I'll show you both. If you know that intensity is proportional to amplitude square, amplitude you already know is going to increase by 2 times because it's doubled now. From here, intensity ought to increase by 4 times. Because you see you have a square term here. Right? If this one increase 2 times, this will increase 4 times. If this increase 3 times, this will increase by a square term. It will increase 9 times. If it increases by 4 times, it increases by 16 times. Okay, this is something to do with maths. All right. So here I know that amplitude increase 2 times, intensity must increase by 4 times. So what you're getting here is that intensity is quadruple. Okay, it increases by 4 times. They say it's double. This is wrong too. Okay, so C is wrong. It should increase by 4 times. All right. Now, another thing you can also do here is to do something like this. If I know the intensity is proportional to amplitude square, I can say that I2 to I1 is equals to A2 square to A1 square. So now I2 over I1 is equals to 0.4 square over 0.2 square, 0.4 square divided by 0.2 square, you're still going to get 4. So at the end of the day, you're still going to get the same conclusion. I2 is 4 times of I1. Okay, so usually there are two ways to go about this. Either you do it like this, or either you do it like this. The method B is actually more tedious. Method A is actually more straightforward. Okay, so C is wrong. Now that leaves you only answer choice D. Wavelength of the sound wave is actually 1.28 meter. This one you will have to use V equals to F lambda. So here we tell you V is equals to F lambda. They told you the speed already. It's 320. You know the frequency as 250 because you found it here. So you can find out the wavelength. 320 divided by 250 gives you 1.28 meter. So answer is D. Okay. So that's how you do this. Okay, then after that, we move on to that next question. Question 25. Now, a wave of frequency 15 Hertz travels at 24 meters per second through a medium. What is the phase difference between 2 points that are 2 meters apart? Okay. Wave frequency 15 Hertz traveling 24 meters per second through a medium. What's the phase difference between 2 points that are 2 meters apart? Okay, so let me just clear off this part. All right. Okay, so what you want is to find some sort of value for complete wave. So you know frequency, you know speed. What would normally come to mind is V equals to F lambda. V is 24, frequency is 15, and then you have lambda. So lambda is going to be 1.6 meter. This is a value representing 1 cycle. Okay. So they want you to find out the phase difference between 2 points that are 2 meters apart. So what you could do is that your phase difference is actually having a difference of 2 meters between the 2 points. Divide by the value of 1 cycle, you're going to get 2 divided by 1.6. You're going to get 1.25 cycle. The phase difference is actually 1.25 cycle. But you could also say in terms of, if you just look at in terms of fraction of 1 cycle only, you get rid of anything more than 1 cycle, it's actually going to be equal to 0.25 cycle. So the answer here would be they are out of phase by a quarter of a cycle. It might help you if you try to see this way like this. Say this one is my wave, like this. 1, 2, 3. 1.6 is this one. 1.6 meter is this one. So 0.4, if I'm talking about a distance of 2 meters, it will be this one. Okay, remember I told you that you can actually divide your wave into 4 equal portions. So each one here is actually 0.4 meter. So if I add 0.4 more, I will get 2 meter, which is here. All right. So that 2 meter is over here. And then this is your initial point. Right now, you want to find out the phase difference between this point and this point. It is correct to say it is having a difference of a quarter of a cycle, but you can also simplify as saying that it has a phase difference of 1/4 of a cycle here. Basically, you're getting rid of this full complete cycle. You just want to look at it in terms of less than one cycle. Okay. So answer choice is B. Okay, so if this one is okay, then we move on to question 26. You have a wave of amplitude A that has intensity of 3 watts per meter squared. What is the intensity of a wave of the same frequency that has an amplitude of 2A? So again, this one, you can make use of what I just mentioned to you. You can have I is proportional to amplitude square. All right. So amplitude A, amplitude 2A. Amplitude increase 2 times, intensity must increase by 4 times. Therefore, the intensity, the new intensity is 4 times 3, giving you 12 watts per meter squared. Answer should be D. But if you want to do it a different way, I can give you this one. Intensity is proportional to amplitude square. You will say that I2 to I1 is amplitude 2 square to amplitude 1 square. You want to find I2. You know I1 is 3. So A2 is basically 2A. You square it. A1 is just A. You also remember to square it. So eventually you will get I2 is 4 times 3, giving you 12 watts per meter squared. So you're still getting the same answer, right? So A and B is actually going to be same. Sorry, regardless of whether you use this method or this method is going to be the same. Okay. Now, another thing I probably should mention to you is this. If I is proportional to amplitude square, just now this one I mentioned to you, amplitude increased 2 times, intensity increased by 4 times. All right. What if I tell you if I increase 2 times, what happens to amplitude? How many times should it increase? In this case, we will tell you amplitude actually increased by square root of 2 times. Okay, there's a pattern here that you need to be very careful sometimes. If it's I proportional to amplitude square, amplitude increase 2 times, I increase 4 times. This one is very straightforward. You just square whatever the increase is at. But if the change now is the other way around, we tell you intensity increase 2 times, what happens to the amplitude? How much by change? It isn't increasing by 2 times, it isn't increasing by 4 times, it's actually increasing by square root of 2 times. So this one will be clearer to you if you use this. I2 to I1, A2 squared to A1 squared. If I increase by 2 times, that means I2 is 2I1. This is I1. And then this one is A2 squared. This one is A1 squared. A2 squared will be the same as 2A1 squared. You square root this, A2 will be square root of 2A1. Okay, that's why you get this. All right. So just be careful about the change that they do. A lot of times they will do it as amplitude increase by some amount, then ask you to find how much does the intensity increase. But in some rare instances, if the question was to be tricky, they instead tell you if intensity increased by this much, how much should amplitude increase by? That is when you need to be careful a bit. All right. Okay, so 26 is okay. Then after that, there's one part here. I think I just continue to do some more questions for you. You know. Yeah, I think I'll just do a bit more. All right. Okay, now if you just look at the next page, page 2, two light waves of the same frequency are represented by the diagram. Okay, are represented by the diagram. What could be the phase difference between the two waves? All right. So here, it's actually that little same diagram as before. Okay, it's actually the same diagram as before. This one is, I think in the example just now, I gave you this one as red, and then this one as blue. They're asking you to find the phase difference between 2 points. Sorry, phase difference between 2 waves. So you needed to pick 2 different points. You need to pick 2 similar points on both waves. So what I mentioned was that you could pick the crest on the red wave. If you pick the crest on the red wave, you should be picking the crest on the blue colored wave too, which is this one. Okay, so what is the phase difference between the 2 waves? That one I mentioned is this one and this one, right? Okay, so if I look at this one is going to be 1 cycle for the blue colored wave. I think I may have done some small mistake just now. Let me just write it out for you. This is 1 cycle. This part here would be 90. This part here would be 90. Okay. And this part here would be 90 and 90. Right? Okay, this one is 200. This one here is actually 90. This one here is actually 200 minus 90, giving me 110 degrees. This one here should be 360 minus 110, giving you 250 degrees. Okay, there's some mistake here just now with what I explained. Just now the notes, there was one example, right? Under page 6, which is this one, correct? The ones that I did for this one, I told you that the first phase difference was 90 and then the second phase difference was 270, correct? There's a mistake in what I did just now. I wasn't looking at the values properly. I said that this part here was a quarter of a cycle, right? Because I assumed that this point here was exactly right over here, so that you get a quarter of a cycle. Wait, no, sorry, not this one. My mistake was that I assumed that this point here was exactly over here, so that you get a quarter of a cycle. But this one is not clearly over here. It's actually here instead, 200. So there's a slight mistake in what I just did under the notes. I think you can just do a little correction from there. So the first phase difference is not a quarter of a cycle. If you look carefully, this one here is 90. This one here is 200. So the phase difference is 200 minus 90, giving you 110 degrees. The previous one I mentioned was a quarter of a cycle, giving you 90 degrees, right? That is wrong, because this part here is not exactly here. Okay, it is at 200 degrees. It's slightly more. So this part here, just change it to this. And then after that, the second phase difference, I mentioned to find the other corresponding value, just take the value of a full cycle minus off whatever you have. So I say it's 360 minus whatever you have. In this case, it will be 360 minus 110, giving you 250. Right? Yeah, I'm not doing this right. 200 minus 90, 360 minus 110. I'm going to get 250. Right, but the answer choice is not here. What's wrong? Huh? Wait, now let me just open up. Yeah, this was one of the difficult questions. June 15 P12. Let me find out what I did wrong here. So, question 24. Oh, I use a different point. Okay, wait. I use this point. It's supposed to be 360. And this part here is supposed to be 90. Okay, let me clear out everything here. Oh, okay, I think I know why already. Okay, this one here, the crest is not at 200. Okay, the point that I pick is not suitable. Okay, because I picked this point here, again, I assume it's at 200. Okay, if you use a ruler to extend the line, this one here, the crest is actually not exactly at 200. If it was exactly at 200, and then I want to find the phase difference, I could have said it's 200 minus 100, giving you 90. 200 minus 100, giving you 110. And then other than this phase difference here will be 250 degrees. But you see, none of the answer choices are here. So I actually picked the wrong point. Okay.
Oh, wait, isn't 200 minus 100 equals to 100?
Sorry?
Isn't 200 minus 100 equals to 100? Then the other will be 260, so we get the answer.
200 minus 100. Wait. Did I minus wrongly just now? Wait, no. Is it? Yeah, 200 minus 100 is 200 minus 90. Sorry, just now I wrote 200 minus 90. Okay, this one was what I wrote. 200 minus 90 is equal to 110. So 110 and 250, they are not in these answer choices. The only way I can explain why is it like this is actually the fact that 200 does not correspond to the crest directly. Okay, that is where the mistake came from. The actual way to do this would have been from here. Okay, wait now, let me just clear. You should have picked another set of points. Instead of picking the crest, instead of picking the trough, it would have been better to pick the equilibrium position. So like for here, this one was the red colored wave just now. This one was the blue colored wave. Okay. So rather than picking the crest right now, the mistake came from the part that this 200 does not necessarily coincide with the crest. I just assumed that it coincided with the crest. That's why the values don't match whatever you have in the answer choices. So the better way to go about this would have been to pick the equilibrium position. This part here, the red colored wave, and then this part here, the blue colored wave. Okay. So now if I pick this equilibrium position on the red colored wave, if I pick the equilibrium position on the red colored wave, I must also pick the equilibrium position on the blue colored wave. So you notice that this one is equilibrium going like this. You also need to pick an equilibrium position on the other wave, but also in a way that goes up like that. So I will pick this one as well as this one. Okay, because this one and this one is equilibrium and it seems to be going upright. This one is also equilibrium on the blue colored wave, but it's going down. So this one is not your similar point. You have to pick either this one or this one. Okay, you have to pick either this one or this one. So these are actually your two phase difference. This one here is much clearer in terms of the values. This one is clearly 0. This one is clearly 100. This one is not clear, but it won't be an issue. You'll be able to find out later. The more important one is this 2. This 2 is clearly 100. Okay, so this one is your first phase difference at 100 degrees. So the other corresponding phase difference, which is between this point and this point, is actually going to be 360 minus 100, giving you 260 degrees. So your phase difference for the second one is 260 degrees. Okay, so it's either this or this. So from here, you look at your answer choices. Which of the answer choices contains this or this? It's only answer choice C that has the value 150 not in, 220 not in, 310 is also not in. So the correct one is 260. Okay, right? So this is actually the correct way of doing this. I picked the wrong points and then I assumed the wrong thing. It came from the fact that I'm too used to picking the crest, and then I assumed that the crest is coinciding with 200. But if you look carefully, if you try to use your ruler to draw a straight line, you will notice that the peak is just slightly towards the left. It's just that I assume it's 200. And then that's where the mistake came about. I got a value close to the answers that you have here, but it's not exactly the same. Okay. Yeah, so sorry about that. I kind of forgot about that little mistake. Okay, so for the notes later on, you just make the relevant changes. Now the working is still the same as this. Okay, the understanding is still the same. It's just that I used the wrong point to read. Okay. All right. Okay, so this one is question 24. Then after that, I move on to the next one. Okay, now a sound wave has a speed of 330 meters per second and a frequency of 50 hertz. What's the possible distance between 2 points on the wave that has a phase difference of 60 degrees? Okay, sound wave that has a speed of 330, frequency 50 hertz. What's the distance between 2 points on the wave that has a phase difference of 360 degrees? So a lot of times whenever you see got mention of speed, got mention of frequency, the first thing that tends to come to mind is V equals to F lambda. So V is 330, frequency is 50, and then you get lambda. So lambda is 330 divided by 50, giving you 6.6 meter. So you want a possible distance that has a phase difference of 60 degrees. So your phase difference is 60 degrees. It could be something like this. X over 6.6 times 360, giving you 60 degrees. Because the original equation just now was phase difference between 2 points was basically the difference over the value of one cycle times with 360 degrees. In general, this is in general how you found the phase difference. Find the difference between the 2 points, divide by the value of one cycle, multiply with 360 to get the phase difference in degrees. So basically you have the phase difference already, you have the value of one cycle, you just want to find the difference in the distance. So it's X over 6.6 times 360, you get this. Okay, so 60 divided by 360 times 6.6, you get 1.1 meter. Okay, so answer is B. You could also probably try to look at it in terms of a graph. where we tell you this is your graph right now. A full wave is 6.6 meter. This one represents 360 degrees. So if you have, say, a phase difference of, say, 60 degrees, the distance would be 60 over 360 times with 6.6, giving you 1.1 meter. Okay, you can also do it this way if you wanted to. Either you look at it in terms of an equation, or either you just look at it from a graph. Because a full waveform here is already 360, representing 6.6 meter. If you're talking about phase difference of 60 degrees, so 60 divided by 360 times 6.6 gives you 1.1. Okay, so that one is for this one. All right. Okay, so that one is okay. Then after that, let me just see some other questions that we can do. You know, phase difference, question 2, question 3. Let's just see page 13. Second wave passes point T. Okay, right. Maybe we try and have a look at page 13. Okay. Page 13, June 2016, P21. Okay. June 2016, P21, page 13. So what the question said here is about intensity again. Let me just do this. Okay. Right, now the variation with time t of the displacement y over wave x as it passes point P is as shown. Okay. The intensity of wave x is I. Use the figure to determine the frequency of wave x. So whatever you have there, wave x was basically this one here. They want you to determine the frequency. So you can see very clearly that this one here is one period, which is equals to 4 milliseconds. So frequency being the reciprocal of the period, you're going to get 250 Hertz. Okay, so this one is okay. It's got 2 marks. Okay, then after that, you have B. A second wave Z of same frequency as wave X also passes point P. Wave Z instead now has intensity of 2I. The phase difference between the two waves is 90 degrees. On figure 9.1, sketch the variation with time t of the displacement y of wave Z. Okay, so right now, you have another wave Z. It also passes through point P, but it has an intensity of 2I. The phase difference between the two waves is 90 degrees. On that figure, sketch the variation with time of the displacement y of wave Z. All right. Okay, so your point P is here. You again now have wave X. You again now have wave Z. Both are moving towards that point X. All right. So wave Z will be having a 90-degree phase difference than wave X. The amplitude of wave X itself, sorry, the amplitude of wave Z itself would be different than X. Okay, this one was point P. So how do you know what's the amplitude of wave Z? You need to make use of this equation. I is proportional to amplitude square. This is the situation that I was mentioning just now. Sometimes they may not tell you what how the amplitude has changed and then ask you to find how the intensity changes. Sometimes they can do it the other way around. They tell you what is the intensity now, and then they expect you to find out what is the new amplitude. Okay, so one easy way right now would be to use this one. I is proportional to amplitude square. Iz to Ix is Az squared to Ax squared. Iz is 2 times of the original intensity. The original amplitude of X was 2 centimeter, because you can see it from here. In the original diagram, the amplitude is 2 centimeter. Okay. So from there, you can now find out what is Az. Az would actually be 2.83 centimeter. Okay, the wave Z would be 2.83 centimeter. Okay, if you want to do it differently, like the way that I mentioned just now, you can. If I say amplitude increase 2 times, it's an intensity increase 2 times, amplitude must increase by square root of 2 times. So in amplitude of Z will be square root of 2 times with 2, giving me 2.83 centimeter. It can also be done like this now, okay? So it doesn't matter which one you want. Either the first one will do, the second one will also do, okay? So you know that the amplitude of wave Z is 2.83 centimeter, and you also know that it has a phase difference of 90 degrees, okay? So by how much difference should your wave be shifted by if you want it to have 90 degrees phase difference? So if you look back at the original diagram over here, the green colored wave is your original wave. Okay, if you have a phase difference of 90 degrees, how many fraction of a cycle is it? Is actually a quarter of a cycle. All right. So if you look at this green colored wave here, strictly speaking, one cycle is here. It's all the way until here. You can divide it into 4 equal portions. This one each represents a quarter of a cycle, or 90 degrees if you would. All right. So if you want to have a wave that is shifted 90 degrees away, for phase difference between two waves, remember I told you, you always tend to look at 2 points that are similar to each other. So if on the original wave, I look at the crest for wave X, wave Z, to have a phase difference of 90 degrees, the crest of wave Z must be shifted by quarter of a cycle, 90 degrees. So right now, wave Z would be this one, okay? If I pick the crest as my reference point, I need to shift the crest by a quarter of a cycle or 90 degrees. So my crest starts here, okay? And then after that, I can just draw out the same shape, okay? Now, how do I know they are going to have the same period in the first place? It's because my question here mentioned wave Z has the same frequency, okay? This statement here. Second wave Z has the same frequency. So same frequency, therefore, same period. Okay, same frequency, same period. So I shift the crest. When I want to draw wave Z, I shift the crest by 90 degrees, and then I just draw a waveform that has exactly the same period as before. Okay, and also I make sure that my amplitude is 2.83. or 2.8. So 2.8 is here. Okay, so make sure you draw your wave Z with an amplitude of 2.8 and your crest being shifted by 90 degrees. And also make sure that it has the same period of 4 milliseconds. I can see from here if this is my crest, and then this one again is my crest. This one is period of 4 milliseconds. All right, so that part is for this. Okay, so then after that, that one is done already. Okay, so the marking scheme says you must have curve with same period and amplitude of 2.8, which you've done, which I've mentioned. Your curve should be shifted 1 millisecond to the left or right of the wave. Yeah, that's what I did. Okay. The marking scheme says shift your graph by 1 milliseconds like this. It's actually shifting by a quarter of a cycle. How they arrive at 1 millisecond was 1/4 of the full period is 1 milliseconds. That's why they say shift the graph by 1 milliseconds. Okay, 1 millisecond is representative of a quarter of a cycle. Okay, so far so good. All right.
That means it doesn't matter whether or not you move to the left or the right.
If you
Or
move
like,
it,
if you move it to the left, it looks different.
if you move it towards the left, it's a bit hard to draw, right? I mean, wait on. Okay, this one is your crest. If you move it towards the left, I think it's still the same, right? Okay, in my case, if I pick wave X is this one. I pick the crest. If I move it towards the left by, sorry, the right by a quarter of a cycle, this is what I get. Now you want to move it by a quarter of a cycle towards the left, this one, the graph is already ended. You have to choose another point. So you would have to choose instead this point, right? So let's just say you move it a quarter of a cycle towards the left, but now you're picking the equilibrium position. So on the other wave Z, you will be starting with the equilibrium position also. Since your reference now is the equilibrium position going down, the new wave that you draw will also be the equilibrium position going down. Okay, it'll be like this, no? Okay, it'll be equilibrium position going down. It'll be like this, the direct opposite. Okay, you get what I'm saying?
Yep.
Okay. If you want to shift it towards the left, going a quarter of a cycle, if you try to do it with the amplitude, if you try to do it at the crest going back, it's a bit hard to see. So you will have to choose another point, the equilibrium going downwards. So since you choose the equilibrium going downwards and you want to shift it a quarter of a cycle, the new wave that you draw will be at equilibrium going downwards, giving you this shape. So this is also another possible shape now. Okay.
Okay.
All right. Okay, so that one should be it. Then another one, I think, let me see one question. Question 17, page 25. Okay, the other one that you can probably do as your homework is probably page 17, question 25. Okay, this one I think I drew it as a difficult question. Okay, it's already 3:30. Should we end the lesson here and then I give you the homework, or do you want me to go a bit more?
Yeah, sure. You can just give it to me as homework.
Okay, so I'll just give you a bit more. Okay, question 25 here is a bit difficult, I think. Right, so we go through this, see whether we can do this. Okay, the graph shows here the variation of with time of displacement x of a gas molecule as a continuous sound wave passes through the gas. The velocity of sound in the gas is 330 meter per second. All the graphs below have the same zero time as the graph above. What is the displacement time graph for a molecule that's a distance of 0.16 meter away, further away from the source of sound? Okay, let me see this one. This one is November 16, P11. It will probably be at the middle of the page. Okay. Yeah, this one is more of the difficult ones. Okay, so the graph that you have here shows you the displacement time graph of a gas molecule. All right, this is the displacement time graph of a particular molecule inside the gas as the sound wave passes through it. Okay, and then now to tell you all the graphs below have the same zero time as the graph above. What is the displacement time graph for a molecule that's a distance of 0.61 meter away, further away from the source of sound? Okay, yeah, this question, there's a reason why I mark it as difficult. All right, so let's just say that these are your gas molecules lah. All right, yeah, particle A, B, C, D, E, F, G, and so on and so forth. All right. So right now your displacement time. So right now what they mention is that you have a sound wave that passes through the gas that causes your particles to displace. Okay. So right now they say they pick out a single gas molecule. Let's just say this is at time t equals to 0 right now. They pick out a single gas molecule and plot its displacement time. So maybe they choose particle A right now. And then they plotted the displacement time graph of particle A, which in turn gave you this. Okay. So right now they mentioned to you, what is the displacement time graph for a molecule that's a distance of 0.16 meter away from the source of the sound? All right. So they want you to plot the displacement time graph for another different molecule that's a distance of 0.1665 meter away. Up to this point, you understand the question?
Yeah.
All right. So they want you to plot the displacement time graph of another separate molecule that is a distance of 0.16 meter away. So what you can do here is that they've already given you the value of your velocity. You can also find out the value of your period here. Okay, so what you do is that V is F lambda is 330 divided by 1 over the period, which means it's over 500 times 10 power minus 6 times with lambda. Lambda is actually 0.16 meter. Surprise. Okay, it's actually exactly the same value as here. So right now what they're asking you right now is you pick one particle that is 0.165 meter away. It's actually asking you to pick a particle that is one full cycle away. So if you look back at this portion here of your graph, one lambda would be somewhere like this, right? I think the color that I use is a bit unsuitable. One lambda would be this one. Okay, this one is my lambda, 0.165 meter. Okay, so just now I mentioned that this one will be t equals to 0. This is your kind of like your displacement distance. It's kind of like your displacement distance graph. So right now this is the shape you have for t equals to 0. You want to pick a particle that is 0.165 meter away, meaning to say you want to pick a particle that is one wavelength away. So it will be a particle here. Okay. So at t equals to 0, this particle is what you want to choose. Okay, now at t equals to 0, the displacement of your particle is also still 0, right? It's actually going to move the same way as this one. Okay. Right, so because it's one wavelength away, one cycle away, this particle will move in exactly the same way as the original particle, because they are having a phase difference of 360. Remember just now I mentioned to you, if you have phase difference of 360 or they are in phase, the particles will always have the same displacement. They will always be moving in the same direction. Okay, so this particle oscillates the same way. All right. So if this particle right now is oscillating like this with respect to time, you also expect this particle to oscillate the same way. So the answer for this would be D. Okay. You notice this graph is exactly the same as what is given above. It's the same. Okay. So let me just write it better. Let me write out first. Maybe I write out the explanation. At distance of 0.165 meter, the particle is a full wavelength away. So therefore, the particle oscillates in phase. Okay, it's a full wavelength away, phase difference being 360 degrees. The particles oscillates in phase. So when you say something oscillates in phase, same displacement, same direction of motion, continuously. Okay, so therefore your graph shape is like this. Okay, can